Hello everyone. Is it on? Okay. Hello everyone and welcome into yet another live stream. Yet another Make It Has No Friends, so write a math paper, okay? Right, yeah. We are writing back to writing today again. Let me just play some really good copyright-free electro swing by Odd Chap in the background. Because I just feel like it fits the mood. And yes, now, the problem with our previous math paper is that it wasn't really a paper, it was just me doing notes and coming up with stuff. So right now, we have a problem. The problem is rather simple. It's a mess. It's a huge, massive mess. And because of that, we have to rewrite it. This time, hopefully, a bit more mathematically. You see, in the first note, this is the best way, by the way. In my opinion, this is the best way to approach things when it comes to thinking about stuff. First of all, you have to write the note paper or whatever, note, whatever, where you have really loose equations, which means equations that you don't actually prove, you are just coming up with them all the time. And then in the end, if everything makes sense, then you can actually prove everything. That's good as a test, it's kind of proof by contradiction, but the entire paper. Then, if you've done it, then you know what works, what doesn't, and what you should study further, what you should just give up, and then you can go for actually writing something like hyper-operational mathematics. Mathematics lowercase because actual mathematics should be uppercase. Yeah, I did that only to correct my stream. Anyway, yes. So, let's do it. Oh, I missed this. There will be one more paper that I'll be writing soon. Okay, not a paper. I'm calling them papers because, you know, I'm writing them. So, let me first check if it works. So, first, introduction. Did it work? There's a table of contents here. I have no idea if it worked. Options. Oh, it does work. Festive. Why is it underlined? Yuck. Can I edit this somehow? So that it wouldn't be underlined. There we go. Looks much better. And this should be Arial Times New Roman. Because I want to be professional. Times New Roman. There we go. Introduction. Heading Y. Heading. Okay, great. Bold for a heading. Introduction. So, oh my goodness, why are you switching to Arial all the time? In hyper-operational mathematics, there are... Oh, yep, because I didn't do it uppercase. Well, I have to live with that. Alright. In hyper-operational mathematics, there are only 3 equations used as a base for everything. Let me just my phone. Fix with the thing. Fix. Down it. There we go. There are only 3 equations used as a base for everything. First one will be operations, which will be, then we'll have anti-operations and hypo-operations, because if I'm not mistaken, that's the antonym for hyper-antonym. That's not antonym for hypo. Yep, I remember correctly. Hypo-operations, which will be... There we go, that's perfect. Now insert an equation, if you wouldn't mind, and that would be x up arrow y is equal to z. Actually, a, b, and c is better here because that's usually used for constants. And only one up arrow because we want a simple example. Now then we have anti-operations, which would be down arrow, and hyper operations, the most confusing of them all. Really weird ones. Latex arrows. Latex arrows. Never remember which arrow is it. The up and down arrow. Actually, we could do them. Here's the thing. Here's the thing. The hyper operation. There's a problem with it. There is a problem with it, which is rather confusing. You see, yeah, that's something. When I went for a walk today, that's all I thought about. The hyper operation. There's something off about it. And the only way to visualize it is with paint. The only way to show it. So, if you wouldn't mind for a second. Paint. You see, here's the thing. When we have a to the power b is equal to c, then a hyper operation for it, logarithm, logarithm base a c would be equal to b then, right? The problem is that for some reason I just assume that hyper operations are in relation to hyper operations. What about anti-hyper operations? Is equal to c. Well, log base a c would be then equal to 1 divided by b. Which means there is some kind of connection. But if we take root log, right? I don't know what to call this operation. Just log vyhat of a to the power c. I mean a, which would be c. Then that would give us back b. And so there is some correlation between them, because that would then mean that L hat would be equal to 1 divided by log. The problem, the one thing that's very annoying about this is that when it comes to not very basic operations like multiplication or addition, I'm not calling them not very basic because multiplication and addition are commutative, which is very annoying. We only have exponents, which means we cannot really observe anything interesting. I will have to spend one live stream just trying to figure out why is exponentiation not commutative when addition and multiplication is. But yeah, so that is interesting. Might be useful to view further later on. So hyper operations will be just up arrow. Hyper operations, yeah, because these are different. There would also be a possibility of a fourth main operation, the anti-hypo operation, which would work like hypo operation except for the anti-operations. Yeah, cool. So now all we have to do is define all of them. We can say that the base hyper operation, which means addition, would be a primitive, right? Let me check. Primitives, mathematics. What are primitives? Wow, this is a huge disambiguation. I don't think there's any of them. No. No. basically what I'm looking for is just some things that don't require definitions, because when you have a field, any field, if you take that, should I waste time explaining this? I mean, I'm wasting time already, might as well waste time explaining this. Cool. So if you have three different things, right, A, B, and top 10 things, A, B, and C, was that, then you can say that A well, yeah, let's do it the simplest way. A, based on A, we can say that B. Based on B, we can say that C. And based on C, we can say that A. That is our first option, which means that all of them are either true or all of them are false. There's no third option. Or we can say that based on A, B. Based on B, C, and we just say that A is true. A is true, because we just say that. Then, if we assume that A is true, we can say that all of this is true all of the time, unless our assumption is wrong, but assuming that our assumption is wrong is kind of weird. Questioning the assumption is good, that's science, that's how you do things, but assuming that is wrong was at the same time, assuming that we're wrong about it being right is a bit hypocritical. That's why we don't tend to do that. Alright. Hyper operations. All operations are defined as followed. For three constant integer numbers A, B, C. Integer numbers A, B, C, we say that A operated B is equal to C, then A, then C is equal to A. Right, so A to the power B is equal to C. That's the easiest one because these are non-commutative, right? A to the power B would be equal to C then, right? Then A, if we are trying to figure out the root. Oh my goodness, why I need more coffee. If I'm having trouble with something that simple, then yeah, I don't think this will go well for me. C, this should be A, this should be C, and this should be down arrow, right, and then base A, up arrow, A to power A to which power will give us C, and it will be B. Yes, and so because of that, this on any three pieces of information, any three out of any three pieces of or any three pieces of information. I feel like there would be a better word to describe it, right? Any three pieces of information, we can get the fourth one. We can calculate the remaining fourth one. The four pieces being values A, B, C, and the type of operation. Yeah. Another very, I should also do these, right? Very important principle, or an important, very important quality aspect, very important. My goodness, what's wrong with me? Aspect of hyper operations is evolution. What they call it in the original paper, by the way. Hyperoperation mathematics, that's much better. In the original untitled document, yes. What they call it, the tier index, operation index. Is it a good idea? Yeah, this is the guessing. This is the guessing definition. Is evolution. Every operation have its own index, and we can evolve these hyper operations using, this is very important, by the way. I'm saying hyper operations, not operations, because there is very important. You cannot do the same thing to hyper operations as to any other operation. Let me show you my right. Something. Okay, great. So because when you take a times b, right? A times b equals c, and a times a is equal to a squared. Then in this case, you cannot say b, a divided by, this is a different scenario, by the way. A divided by b is equal to c, obviously, otherwise it would be 1. A divided by b is equal to c, and then a divided by a is equal to the root of a. Because that's not really true. That's not really true. It just so happens that a divided by a is constant, which is rather annoying. Fortunately, this is very annoying because roots then are very problematic. Using the following equation, I would like to center this, please. There we go. Which means a up arrow n up arrow a is equal to a up arrow n plus 1 up arrow 2. Yeah, which basically just means that for any operation index n, there is an operation index n plus 1, I think this is necessary here, n plus 1 which is based on the previous operation. Previous hyper operation, also important. Hyper operation. Yeah, what else is there? What else would be there? Another very important aspect of hyper-operational mathematics is the generalization of any operation. You have to define every operation in the same way regardless of its index. Because of that, we have to assume that I didn't even say what hyperoperations are, I just realized. I feel like I should mention this in the beginning. Hyperoperations, anti-operations, hyperoperations. Space for everything. As an example of what that means, we can compare it to normal mathematics. Now, we can just say, is there a shortcut for centering? Control Shift E, useful. So A B would be equal to A times times B. There we go. That's two up arrows, up arrow. This would be also in the end. Over here we would have is equal to A plus B, like this, and so now the two curious things, which means A up arrow B, actually A plus A, be equal to A plus A, there we go, A up arrow, A would be equal to A up arrow 2. Now A plus A would be equal to just 2 times A, which is equal, yeah, this, cool. No more mathematics. That's nope. We need left. L. Why is E? Wait, what? Which one is right? Ah, left, right, enter. Why not C like center? Control of C is already doing something else, right? Makes sense. That is actually very, It's quite the thing to show. This. This case in this case, based on that, we can say that first index hyper operation is addition. First index hyper operation is addition. First index. There we go. First index anti-operation is subtraction. Second index hyper operation is multiplication. Second index anti-operation is division. Third index hyper operation is exponentiation. Third index anti-operation is that's a good question. Opposite of exponentiation. Not well, no. Wait. Wait, what? How in wait? No, that is so not true. If you have a to the power b equals c, then logarithm gives you b, and we are usually looking for the a, which is roots. But what happened to this, by the way? Oh, that looks like the. Oh, Google, what have you done? What have you done? What have you done? What is this? Why have you done it? What's the name though? That's what I'm wondering. Alright. Exponentiation. Yes, thank you. Wikipedia, what would I ever do without you? And irrational exponents, real exponents. They're actually very interesting. That is very interesting. That is extremely interesting. That is so extremely interesting. Ha ha ha. Wow, so I had no idea about that. There's no zero algebraic extensions. If b is any algebraic number, in which case all values bx break, if x is irrational, that is not rational. Okay, I got that. And both b and x are algebraic, says that all values of bx are transcendental. Not the root of any non-zero polynomial of finite degree with rational coefficients. So that is extremely interesting for so many reasons. For so many reasons. Exponentiation. Yeah, well, yeah, what I was looking for, I just remembered. I was looking for the opposite. What is the opposite of exponentiation? Bing GPT, tell me. There goes my coffee. Almost. Still have a little bit left. Very delicious. Just normal, horrible tasting coffee with added cinnamon and milk. That's neat. The opposite of exponentiation is logarithm. Just as division is inverse of multiplication, it is not though. It is not. It is so very not. Okay, listen, mate. Tell me that. A times B is equal to C. A divided by B is equal to... Well, no, that I did that wrong. A divided by C divided by B is equal to A. So we basically we do this. Right? So that's what we are looking for. Which means A to the power of B is equal to C. We are looking for something that will turn this round. Which means that C operation, some operation B would be equal to A. But logarithms, log base C B, does not give us A in this case. Does it? It gives us... No, it doesn't. It's so not true. It is so not true. No. If adding is addition, multiplying is multiplication, and exponents are exponentiation, yeah, definitely expensive, then what are roots? Looking for roots, the root of the issue. 20, by the way. That's not what I was asking for. Inverse operation exponentiation. What is the inverse of exponentiation? Bah. I am so close to having a breakdown. This logarithm of number is the exponent to which another fixed number, the base, must be raised. I know what logarithms work. I know that they are also not the inverse of exponentiation because the movement is different. In order for a logarithm to be valid, in order to get back the a, because we are trying, unless I guess we could also switch. No, we have to switch it this way. That's the only way to do it. We can also move everything one forward. which would then give us CAB combination, which is not CBA, so it still don't work. Yeah. The government's feeding you lies. That's what's happening. Roots. Yeah, I got that much. If we can generalize the rules of all the hyperoperations, then that's amazing. Muff. Great, so big, thank you. Great. I am... is... rooting? What is the act of performing a mathematical root? Radicalization. That was so hard to find. Like, if not for AIs, I would have never found that. Progress of causing someone to adopt radical position. Nope, no. Mathematics. Process which people come to adopt. Nope, not what I'm looking for. I'm looking for the math. I'm looking for math radicalization. No, did Bing just lie to me? Bing, you lied. Okay, I may be wrong, but why aren't there any sources? Could you give me sources for the last answer? I always remember that the answer is spelled not like it makes sense, because S is in the middle, which is weird. That's a probably statement. I'm sorry, but I couldn't find. I mean, at least it's honest at this point. Let me just add to MK I love using Bing. I should probably screenshot the entire thing. There we go. Yeah, I love Bing. I love Bing. I mean, at least it's honest, right? I really want to actually give me a second. Downloads. Actually, you know what? Let's create a post on. Oh, by the way, Soda released a song called Leap into Battle, if I'm not mistaken, on my channel community page, so I can't recheck it, but it was with Leaping and Battle, I remember that much. And it's fire. It's just absolute fire. Image, say from computer, download. At least it's honest. Remember that anyone can see your post. I know. I have to post more. I'm not posting enough, you know, like those influencers. So what now? Now that we've gotten nowhere, we ask the question again. Let's see. If based on the previous things, I'm pretty certain it takes in the previous. Finding the radical. Mate. Finding the radical of a number. Radicals. Great. Radicalization is very it's very tempting to say that, but it would be just straight up incorrect. I am okay, great. Anti-operation is finding the radical of a number, the radical of a number, or basically that's wrong, then wrong thing. And for the first time, third index hypo operation is logarithm. What is really interesting about this is the lack of hypo operations in the first two indexes, and that is for a very specific reason. Addition and multiplication are commutative, which means hypo operations are not required, because I need to copy another. Give this. If A times B is equal to C, then hypo operation will be ACB, which means A times B is equal to C. We are trying to get the B, which means we divide C. Those we divided. Those way to divide it. No, I would prefer the better version like this. C divided by A. Because of that, there is no need for hypo operations. This will give us B. There's no need for hypo operations for addition and multiplication, because they are commutative, which means division works just fine. By the way, I am pretty certain I messed this up. Base A. Base is the other way around, which would mean it would be CAB. Because it would be CAB, which means it is the opposite of a hyper operation, technically. Yes, it is an opposite, that's why hyper. Yes, it's CAB. It just logarithms are written down in a weird way. Which means we get the result, we plug in the original, and we get the operee of the operation. Great. Which works just like a hypo operation. Just like a hypo. And quite, because yeah, I can just leave it at that. Another very important aspect of hyperoperational mathematics is generalization of any operation, to mean that we have to define every operation in the same way regardless of its index. I should probably add some subheadings here for This is introduction, which means we should probably add operations. There we go, and basic operations. Where's the arrow? That's wrong. New times New Roman. Times New Roman. There we go. Much better. Operations, basic operations. Then we will have an evolution. Why Arial? Times New Roman. Much better. There's this, and then generalization. Let me spell it. Probably. We have to assume that addition and multiplication or in order, that's what I called it, order first and order second. I should add as a disambiguation so that later on I wouldn't have any problems. Index. On index or order. And again, evolve using following equation. Yeah. or the first and second order hyper operations are not commutative. This means that we can define any equation using an unknown order hyper operations, and it would work everywhere. It also has the really nice bonus of working sometimes when working in cases which no conventional right mathematics, I'm still calling no mathematics right now, I think what I'm writing here is madness, has to use exceptions for. Like the really nice fact, really nice exception that multiplication is commutative unless you go to quaternions, which I should probably write down here. Would work everywhere. Really nice added bonus of this approach is the fact that we wouldn't have to use exceptions. For example, in conventional right normal mathematics. No, that sounds sarcastic. I don't mean it sarcastically. I still believe no mathematics is objectively right, whilst mine is objectively wrong so far. Well, I haven't done anything yet. When we get to the fixed points, half functions and omegas, that's when I have done something, not much, but still something. In conventional mathematics, the rule is simple. Multiplication is commutative. But it has its own exception. Quaternions. multiplication is commutative for any real, imaginary, or complex number, but its commutativity breaks down when quaternions or octennions or unrecognized word. Really? That's interesting. Octennions? Did I misspell it? Octanions? Octans? Nions? Octonian. Octonians. I'm sorry, I'm not really used to using octonians every day, so it just so happens it's something that I don't use that often. Non-commutative, non-associative, that's the added bonus, but we won't get into that for now. Hypercomplex is just above complex numbers. Finite dimensional algebra of real numbers. So, or any high dimensional hypercomplex number system. Other higher dimensional hypercomplex number system is introduced. There we go, great. So yes, I really like that. I really like that it's I think I confused my Google. I think my Google Docs might be ever so slightly confused. Its tone is really hard choice. It's or its. Yeah. That's interesting. Which one is it? Well, it is. It's. Oh, it's. I could spend an hour doing this, honestly. That would be a fun live stream. Oh, wait, do it. Yeah. I guess it's time to go back to math, right? Yeah, so. Generalization. That was our table of contents, by the way. There we go. Oh, we just have to update it. So much more sense. A lot of stuff. A lot of stuff, not a lot of pages, but to be fair, all of these are rather simple. So it doesn't matter. But it's cumulativity because it's only higher dimensional complex number systems. But nobody tell me it was plural are introduced. Because of that, we have two options. First one, assume that non-commutativity is a rule and multiplication and addition is just with multiplication and addition as just an exception, or the second option, say that commutativity of multiplication in complex numbers is just a coincidence. It's just a coincidence. I'm not used to writing coincidence. I'm sorry, I'm a scientist. Yeah. What do I mean by the second? Well, let's write down. What do I mean by coincidence? Should be obviously, whoa. That's a string. That's also a really neat shortcut, keep in mind. What do I mean by coincidence? I mean the exact same the exact same type of commutativity as in just center this. There we go. A to the power, nope, that's not power. A to the power b is equal to b to the power a for a equal to t to the power 1 divided by fraction. Oh yeah, it works. 1 divided by t plus 1. Okay, I need to consult. Black pen, red pen. A to the power b is equal to b to the power a.
Thank you for this time, this teacher.
Obviously, wait, why am I not? Oh, a different channel. I forgot. Oh, that's a different video. It is a different video. Yeah, not the one I'm looking for. I'm looking for the one with the exact solution for which, or maybe it was x to the y. It might have been x to the y and y to the x. Yes!
I know many of you guys know this already, but we have the exponent. And
There we go. I remembered it. I remember that. Yes, so we had t to the power. Yeah, that's right. We had t to the power 1. It's minus. That's the one I wasn't sure about. And then the second one, which is just t 1 minus t minus 1. Yes. For multiplication, it would just look like this. Why though? Why would you? There we go. Look like this. Oh, this is awful. There we go. Much better. Times b is equal to b times a for a which is equal to x0 x0 plus ijk, those are, yes, plus x1 j I plus 0 k plus actually 0 j and b, except with this as a 2 and this as a 3. like this. And because of that, we just assume that multiplication and addition are non-commutative, except they just happen to be commutative when walking with complex numbers. There we go. Sick. Done 3 pages. Looks pretty decent, I'm not gonna lie. Much better paper. Now we need this second. This, which would be numbers or omegas. What to call it? Omegas. Omegas. There we go. This should be still in the introduction, actually. So like this. And not Arial, preferably. Yeah, that looks much better. Because omegas are still kind of part of the introduction. I haven't done much more than just introduction, honestly. So omegas. So far, we talked a lot about operations and not a lot about the operies. Operators. Operies. And so that's Arial. So it is finally time to introduce all sets of numbers in high operational mathematics. Omega n. Just like everything else, it should look actually like this. Yeah, because it will be very annoying. We'll have to change the theory a bit because it doesn't fit. It does not fit. Our omegas existed in relation to anti-operations. And it just so happens that doesn't fit. You see, if you have an irrational number x and you raise b to the x, as we've read a couple of minutes ago, we get a transcendental number, which means we get a number which is not quite irrational in no way. We have to read this theorem. We will have to. This will be very fun. Let's just, for now, say that the default omega will be in relation to anti-operations. Hyper-operational mathematics. Omegas exist in relation to orders, where 1 omega is a set of all integers what's the symbol? Z or I? Wait, why Z? Z? I, alright, great. We need that. Well, integers. Equation. Omega 1 is equal to integers. And now the fun begins. Oh, sorry about that. Based on that, we can define all the other omegas a very simple way. I do believe this will look better actually on the left. Omega second will be equal to omega second will be equal to well, we would need O notation for this. How do I note that here? How do I note down? Was O's. That's how. That's also a good way to do it. How would it look like on center? Terrible left, I was right. And then all we need is define one more, this. Or actually, no, I think I prefer 11. Except these could be over here. Oh wait, we already have it, yeah, so this actually can be down like this. And then basically means that omega n n n. That's it. So for any, shouldn't probably do it in Arial. So for any, anti-operation with order. Arrow and down arrow. Actually, I should probably write down differently. So I just have to grab something with the. You can reach with the N or lower. Anti-operation. Then now we should probably add the O, right? So this should be actually numbers. O and omegas. Like this. And now we should add the OHATs. What should I call it? Numbers? Numbers, omegas, O's. OHATs. This should be times New Roman. Based on that, we can create an equation for getting any number in a given set, denoted by the equation in a given set based on integers. So for example, and then we would need this to the left, so it would be rather big. Actually, maybe center would be better, we'll see. Hat O1 is equal to the first one integers, so just x0, then second order would be equal to this down arrow, I already made a mistake. Down arrow, we have to generalize x1. Almost messed up already. X2 down arrow x1 x3 actually. I don't know why. There we go. Now we have O2, now O3, which will be just longer than this. Down arrow, down arrow, down arrow. This, which would be 4, 5, 6, 7. Or the generalized version. This means n is equal to down arrow, down arrow, down arrow, down arrow, dot dot dot. Then what we need is this exactly. This down arrow arrow, down arrow, this, dot dot dot, and oh my goodness, look how long it is. That's what she said. 3 of these. There we go. Now all we need is 0 and a 3, yeah, then we end by doing n to the power of this -1, right? We should probably add the 4th. Could calculate that, but first that won't make sense. What I'm calculating is alright for doing it. Down arrow, down arrow, down arrow, and down arrow. That's actually sent it. Huh. Guess this. Seven, 8, 9. We should get 15, right? 9, 10, 11, 12, 13, 14, 15, yeah. So this is basically over here we have, yeah, then we have 2 to the power n -1. This is so massive. That's what she said. Then you cannot really see this over here, but I mean, if you zoom in, you might. That's what she said. I'm sorry, I'm just full of inappropriate jokes. My goodness. What's wrong with this 0? Yeah, let me just delete the first X. Or this one, doesn't matter. 4. 3, 2, 1. That's the end. Now it's time for the middle. Middle being obviously no, middle being just more complex. Thank you so much. Great. Can you read that? You can. Sick. Good. That's great. Great news because it's gonna be small. Middle being the same thing, except this is to the second power, this is the first power, this is the 0th power. And this is to the third power, which basically means we take this, and in the middle, write the most important equation. Except -1. That's it. +1. +3. +2. This shouldn't be -1. This should be just the thing. You see, normal people I think would just look for some friends. That's think that's what normal people would do. I'm just... Yeah, I think normal people would just look for some friends. On the other hand, I'm a YouTuber, so having friends is kind of the picture. I'm a YouTuber. There's no worse profession than a YouTuber. Maybe a general influencer. That could be worse. That's the second worst thing, right? Second worst thing right after YouTuber. So having friends out of the picture, which means the only thing left is writing math papers. Or papers in general. There we go. That's some foreshadowing for the future. Space, life and time. That's some more foreshadowing. You're welcome. You have no idea what I'm talking about. Yeah. Well, let me just change one thing, because I'm pretty certain. There we go. That's what was missing. Now the stream is entertaining. Oh, and now I have to read the thing. You know what I have to do right now? The most fun thing in the world. Exponents. Exponentiation, yes. Now what we have to find is irrational transcendence, yes, this. I love it. Will be fun. Gelfond-Schneider-Theorem. Oh yes. Oh, it's not linked on Wikipedia, which is weird. We should probably link it. I do have an account. Mathematics establishes the transcendence of large class of numbers. That is not the root of a non-zero polynomial. Okay, so transcendental numbers. Not a root of a non-zero polynomial. What's really funny about this is that this still means they could be included in some omega. They still could be included in some omega because we are not only talking about the roots, we are talking about hyper roots. No, I still should get a better name for it. We are talking about anti-operations of higher orders. Sorry, I just can't really look at it. Give me a second. Dang it, that's the wrong text. There we go, that's the right one. Outline. Select color black. It's still very much unreadable, but it's better than nothing. It is better, but it can make it even better. Like with outline 20. Yeah, it's better. Now this one also requires a big outline. Like 20 is maximum. So yeah, that's good. I'd say looks pretty decent. So transcendental numbers are not rare indeed. Almost all real and complex numbers are transcendental. Yes, since the algebraic numbers are complex real numbers. Yeah, cool. But history. I care about. Will not follow this multiplication is a proof of transcendence. The idea is following. Assume the purpose of finding contradiction that E is algebraic. There exists a finite set of integer coefficients. Satisfy the equation. By splitting perfecting the form p plus q is equal to 0. Why can't it be written like that exactly? 0 2. Oh yes, it can. That is true. Yeah, sorry, I missed the ends. Obviously, it can be. Then p is an integer times a sum of factorials, which results from a relation. Oh, this is fun. No, zero because of saying yeah. Okay. This is a very elegant and nice proof, but I don't think it's usable for me. It's trying to prove something too different from what I'm trying to prove. I could prove it the dumb way, but I don't want to do it the dumb way. I don't want to do it the dumb way. I want to prove it the right way. We could just say that the set of numbers is always increasing by an infinite amount, but that still wouldn't get us the uncountable infinity. We're looking for the uncountable infinity, which is so upsetting. I so want to prove that. I so want to prove. I so want to prove that. Won't be easy, right? I would love to do prove a contradiction, but what should I contradict then? Well, I should contradict that for any number n. So, okay. So for any number n, right? Let's say that the number n is not in an omega. I should not use n there. I should not. X, let's assume number x that is not inside an omega n. What would that mean? That means that we cannot get number x with any anti-operation, based on any anti-operation on integers. But we can subject the number x to anti-operations, which means we can do x down, y if we want to. Okay, this shouldn't be x, this should be delta. Because I've been dreaming about deltas and omegas ever since I introduced this. It can be subjected to anti-operations, which could be convenient. You know what's really interesting? What's really interesting is that for any number delta. Wait, okay, let me just. No, wrong theorem. 1000 times. Interesting. Insert an equation, please. Yeah, I was writing golden ratio. That's what's wrong. for ring number delta, right? If we add to it some number, come on, give me some other number, alpha, good enough, alpha, then we can get O hat 1. We could define an alpha like that. So that delta plus alpha would be equal to O hat 1. Which means we could, based on delta, create new infinite amount of numbers. No. Huh. The omega delta problem. Every action has its equal opposite reaction because of Hamilton. I shouldn't. Okay, every I should copy insert the equation omega. Every omega n for every omega n there is an omega n plus 1 which n plus 1 which contains omega n. That means that every new omega is infinitely times larger than the previous one. Because every new omega is created by what? Well, then with A, obviously. Every new omega is created by creating n to the power by creating 2 to the power n more combinations of the n minus 1 numbers. But there is an infinite countable uncountably infinite number of numbers. That's... I'm tired at this point, okay? Number of numbers, so... I'm going to infinite number of numbers. So the question is, for any given number delta, is there an omega n that contains it? And now it's time for the really fun proof. Yeah, my Google Docs is just having some issues too, but I also have some issues at this point. All right, time for the proof, the very fine proof. We will attempt proof by contradiction, because it's the easiest one, by saying for a given number delta, there is no omega n which would contain it. So now let's start by introducing alphas, so that delta up arrow alpha 0, alpha 1 actually, for 1 is equal to O 1, then second, the third, and so on. Third, ... Now we have a different question, well, the same question. We have to prove that either alpha, any of alphas, or delta is contained in some omega n, which is fun. I mean, if I prove this, this would be huge. Well, not huge, big, rather large, not small. Omega delta problem. I'm not kidding when I'm saying it. It's really been in my dreams. Those were some very nice dreams, though. Not gonna lie. Alphas. Dot up to alpha n, so that for any n it exists. Great. Now what? Good question. No idea. That means that we can turn this around. Say we could use the really big equation for ON, up it for the alpha on the other side, but that would give us nothing. That would give us an equation for delta. I'm an idiot, by the way. Over here it should be like this. Okay, it might give us something, maybe. This is n, which means if we this down by this, up and A. I mean, I could bring in the big equation for O hat. Implies. Implies. Implies, obviously I misspelled that. Implies. Implies. Or just right arrow. That this, so that's O1, which means delta is equal to up arrow alpha 1 down arrow, actually. Oh my goodness, yeah. I got nothing. Down arrow. I thought I had something, but I didn't. Huh. If you have A up arrow B is equal to C, right? That means in order to get the A, we need this. C down arrow B is equal to A, which is, yeah, that's what I did. So this is an equation for delta. Well, the equation for delta would look like this. Here's where the fun begins. There should be a 2. There should be a 3. Here's where the fun really begins. How the hell am I going to do that? Do this? How? Anyone mind telling me? By the way, over here I totally missed brackets. In here, in here, in here, and in here. Because brackets are unbelievably important in this case, so I'd rather not screw them up. Like this and this, this and this. Everything is not commutative, which means order of operations is, well, important. So it was just straight up wrong here so far. That's great. Now, over here, this will be a pain to write down, so how about we won't? Because, oh my goodness. What now? Well, what now? What's really interesting is that in all of those cases, these are omegas, right? Which means we can just copy like this, for example. And the problem is, obviously, we haven't defined anything about alpha, which, you know, gives us nothing, practically. Practically speaking, it gives us nothing. Absolutely nothing. Fixed points could be useful. Numbers after OHATs, we should add one more thing. It can be small, it's not that important. Fix points. Fix points. Points are just what? Are just numbers that are not affected by, that do not affect not change any operations, so that fudge a down arrow is equal to a. Same thing goes for up arrow 2, and for logarithms, or actually just like this, up arrow 3, and this should be the other way, which means a is equal to this, but not inside the hat. There we go. I do believe that would explain around everything, right? And a only here. Because when you have a log a, then you, well, log a actually, then you get 1, right? So that's the fixed point of it, which is 1. There's one thing that's really interesting to me. So, one thing that's very interesting. So, that would mean that A, up arrow N, up arrow B, down arrow N, down arrow B is equal to A, because that's what anti-operations are, right? Because what basically means is that I can go one move further to explain this actually. That explains it. Right. And that's actually equal to down arrow n down arrow at fixed point n. Okay, that's actually very interesting. Wait, what? Up arrow, up arrow. Wait, can I not just do this? Yes, I can, but it changes nothing. Yeah, right. I realized why only when I won't add it. So right now, if we can distribute the anti-operated B inside the bracket, we would get something very neat. We just have to distribute this. How can you distribute hyper operations? That's a good question. No idea. No idea. I guess we shall see. Let's try it. Let's try distributing some hyper operations. A plus B minus C. Well, that would basically be... There's nothing to distribute. This annoys me so much. The associativity too. Okay, it's fine, right? Then we have A times B divided by C, which is basically A times B divided by C. This is basically equal to A plus B minus C, right? And then we have the third one. Top 10 equal signs. Alright, then we have the third one, which means A to the power B root C. Which, I mean, there's nothing to distribute actually. There's no distributing this. It's just operating. One thing that's really annoying about this is that based on that, B down arrow and down arrow B should be equal to the fixed point. It is not. It is not though. It cannot be. There's nothing to distribute. Well, yeah, over here I guess it is. I guess you could change it to A, B divided by C, but that's not really generalizing, unfortunately. Wait, half functions. You have half function, right? Half function n of A, right? Up arrow n up arrow, half function n A, that's equal to A. Could this be A? One half up arrow n up arrow A up arrow n one half. Well, let's say our A would be 4. If we are trying to get the half of, well, let's say that would be our A. Yeah, so if we're trying to get the half of 4, that would mean that 4 is equal to Over here we already know for addition it will be 2 plus 2, but using our second equation it will be 4. Oh, this should be times. No, it shouldn't be times. It cannot be times. Yeah, what's really interesting to me about this is that 1/2 0.2 should be included in this. Would you like to see why? Let me show you. For powers, it will be 4 to 1/2, or in other words, because this should be plus 1. Plus 1. And plus 1 1/2. Because then what will give us is 4 plus 1 plus 1, because then it will give us 4 seconds plus 4 seconds, which is, yes, that's true. For multiplication, it would give us 2 times 2. I picked the wrong number for this. Let's pick 6. 6 would be better. Right, so let's pick 6. 3 plus 3, or in other words 6 seconds plus 6 seconds. Then we would have the next one, which would be 6 is equal to 2 times 3, which would mean, no, we're looking for halves. Root of 6 times root of 6, which is equal to 6 to 1/2 power times 6 to the 1/2 power, and then the effing tetration comes in to break everything. 6 would be equal to x to the power x, which would be equal to x 1/2 tetrated x times, well, to the power, yeah, it will be 1/2 tetrated x to the power 1/2 tetrated x. But here's the kicker. Here's the fun bit, the funny bit. The fun bit is, it doesn't really work for non-integers. So this is it, right? It's either integer or super roots. I call them hyperroots, and that's a much better name, but whatever, you do. Open question. It's open question. Okay. Tetration calculator. But I need tetration calculator for irrational numbers. Could I have that? That's a good question. Just a base. Base 10. Base the one as a Sheldon's base. Oh, haha. 1/4. 1/4 to the. Okay, wait. Base 10. 0.5. 0.5 of base 10 gives us this number, which means, okay, oh, Desmos. Desmos is good enough for these sort of things. Let's learn together. Cool graphing calculator. A is equal to this. A to the power A. 945. It's close. Very close. Kinda too close to be a coincidence. It's very close. Let's try for 2. Ah, it's so close! What if we add like 1 over here? What if we add like 9? It's so close. It's so close for it to be a coincidence. Can I... Do you have any source for how it's calculated? Approximating method. Is an equation for this. The larger the number, the more it approaches 1? No, the smaller the number, the more it approaches 1. Makes sense. Yeah, like, some weirding me out. It's all so interesting, but can I please get an equation? Slog, that's a great way to call super log. Wait. Fine, let's get the nutrition calculator. Again, that's a good question. Calculators and computers aren't grave recursion. What? Shocking. Titration. So no one answered. 7 months. I'm so glad you took the time to tell him, yeah, your question is terrible, instead of, oh, actually you're terrible, whatever. Just telling him why this is a hard problem instead of giving an answer, because yeah, we all know this is a hard problem. Where it holds. Okay, this will be cheesy. Oh my goodness. Oh, it's amazing. Oh my goodness. Oh my goodness. Wait. Where it holds, yeah, but is there maybe some sort of anything to explain how this exactly works? Oh, it's... No, wait. Wait, what? Excuse me, what is it doing? This calculating the arc tangent of... So as number increases, this no, as number increases, that increases. So. That titration calculator has a bit too many not explained things for me. I mean, this is good. This is a good calculator, very good one. If not for the fact it's kind of missing what I need. Yeah, because 10 to a power of like this gives us 2.477056063449647751. Are those 20 places all correct? Let me just check really quickly. b to the square root of 2, 2 and 4. Wait. Two and 4, which means that... Come on, give me some more space. No, wait. So, to the second and to the fourth, well, second to fourth is equal, these are two fixed points, which means 2 and 4. This is interesting. That means 2 down arrow, 2. Up arrow, up arrow, up arrow, up arrow. 4 is equal to 2. See what happens on lower ones. 2 minus 2 times 4, that's 0. Still a fixed point for itself. That's 4. That's root. So square root of 2. Because these give us fixed points. This is a number by itself. If it's commutative and you apply anti-operation on itself, then you get a fixed point. Now fixed point operated to no matter what. To be fair, you get a fixed point for first one. It's actually 0 times 4, which is 0, yeah. Fudge. There's one interesting thing, there are two kinds of fixed points. There is the A to the fixed point and kind of fixed point, and then there is A to the fixed point stack fixed point, kind of fixed point. The up and down fixed points. There's a difference. In this case, for multiplication, this would be 0. For powers, there's no such thing, unfortunately, because there's only 0 and 1. Yeah, fixed points are a mess, they are not really worth doing anything about. Fudge! It's very annoying because the iteration is surprisingly close to that half thing. It's unbelievably close, which is annoying. Wait, what do I mean graphically? Whoa. Graphically, wait, no graphical. Yeah. Graphically, what does it mean? You have x plus x. Try that for a second. X plus x. Graphically, it means what point is halfway down, right? So halfway there on the function. So for example, in between 0 and that point. So for example, for 3, point that's halfway there is over here. There we go. For x times x, for 3, will be over here. A second. Let me check. Let's do y is equal, and will it cut through 3 exactly? No, I'm looking for just plain old x. Well, it will. Did wrong. X. There we go. Yes. It does go through 3 exactly. That's the graphical meaning of a half point. This half as much length over here as it is over here. Well, half as much over here. Well, this, we have to find a way in which this would be equal to this. It's not volume, definitely. I mean, not the area of the function of volume, obviously. It's not area, which means it has to be something else. Something exciting. Length, how do we calculate that even? Because this curves, which means it would be it would have a different length in theory. It would explain why halfway for a straight line would be equal. We have to find something that's divided in half over here. Let's another black line. For 3. We have to find something over here that we, in between these 3 lines that we divide in half. The first one is obviously longer. This one's more straight though. No, but this one is high up though. Okay, let's treat this in theory as a triangle. As a fun exercise, alright? In theory, let's just assume it's a triangle. We are doing a calculus right now. By doing a calculus, I obviously mean, you know, treating continuous things as not continuous things to make the calculation simpler. If we treat it as a triangle, what will it look like? Well, we would have the first triangle, which would look like this, where this is a square root of 3, and this is, no, where this is a 3, and this is a square root of 3, and we'll have the other triangle, in which this is 3 minus square root of 3, and this is 9. Yeah, 9. Yeah. Looking at this, a squared plus b squared, which means 3 plus 9, so square root of 12. Over here we have 3 minus square root of 3. Okay, my brain is too slow, let's just do it normally. 3 minus square root of 3 times 3 minus square root of 3 is equal to... Okay, my brain is too slow, right? Just give me a second. 9 minus 3 square root of 3 plus... okay, so minus 6 square root of 3 plus 3. Which basically means 12 minus 6 square root of 3 plus 3. Minus 6 square root of 3. And, well, yeah, that's close. I may be wrong, but that would be 36 times 3, right? It was 36 times 3. 36 times 3, root of 108. Which would be equal to 12 minus root of 108. Oh, please tell me root of 9 squared. No, it's impossible. 81, yeah, so plus 81. 12 plus 81 minus root of 108. It would be too perfect if it was square root of 2. Unfortunately, it is not. 93 minus 108. Now, please, magic box, tell me what's the root of 108. It should be somewhere reasonably close. Well, it should be in between 6 and 12, closer to 12, between 9 and 12, still closer to 12, in between 10 and a half and 12, barely over 10 and a half, so in between 10 and a half and 11. 10 and a third, yes. But it shouldn't be higher than... No, that's 73, yeah, right, then 10.3, yes. Which is great, it gives us 80 couple, 82.7 stuff, rounded up. It should be actually 0.660, whatever. Which is not fun. So it's not that. It's not the length. Also cannot be the area, can it? No, it... Maybe. This is getting smaller while this is getting higher. Maybe the area? Well, we can check. We just have to check the square root of 3 times 3 is equal to 3 minus square root of 3 times 9. Which, I mean, very simple calculation, am I right? That's just square root of 3 times 3 with 27 minus 9 roots of 3. Divide both sides by root of 3, right? Then we have 3 is equal to 27 divided by the root of 3 minus 9 divided also by... We could then go 9 to the other side, which means 12 is equal to 27 divided by root 3. I don't think it is. Okay, I don't think it is. I don't think if you get 27 and divide it by an irrational number, you will get an integer. I don't think that's how it works. What's more, wouldn't this be equal to 27 to the negative root 3 power? In which case, that number would be transcendental. Great. So we got nothing so far. Just fun. We would have to... Okay, so that's an assignment for the next time. Find a way in which halves are half of something. Because if we find a way in which halves are half of something, I don't even remember when I started with what I changed since the fixed points. Fixed points, then there was something, and then half functions were important. So let me just add half functions. Half functions. Half functions are functions that return a half of something in relation to a given hyper operation. Like capital this for now. I'm pretty certain that was the first hat I came up with. The H hat. H hat of A, N, up arrow. Let's first generalize it, then we'll do. Like this. Not 12, like this. Dot dot dot. Great. This shouldn't be like, should be for example. There we go. Half functions can also be extended for other pieces of rations. It is fudge. It is obviously. Oh, it's so obviously related to division. How am I so blind? We are operating only on the rational parts of. So operate other rations. Yes. Now let's copy this. Oh, actually, this is enough. Can I please get back on this side? Thank you. Yeah, I know why it jumped so much. Why is it going so high up? I like put it next to the hut, but I can't, apparently. No idea why this included an up arrow. Like this. Other fractions. There we go, that's great. Now, it's so tempting though to figure out what is being halved in this case. Wait. When it comes to the distance, we'll be close. This is a root of 93 minus root of y 108, right? Wait, 108 root, that's 10.39 dot dot dot. What if we divide it into 2? Well, we do need for this. It's just so convenient to use. It would be just so convenient to use some integrals. What we need is length of this, right? So we have to divide this into 2 triangles actually, then into 3 triangles. No, I mean to 2 triangles, then to 4 triangles, then to 8, and so on. What is this? What would this approach? Give me a second. I have to go for a second. Alright, what do we have in, boys? What do we have in? That's a good question. It would be really convenient if I could figure that out. Because, yeah, we would have to actually divide it into 2. Okay. I'm gonna need another one. Which is... So this is the half in this situation. The convenient thing is that for 4, half will always be equal to a 2. Always. That's kind of a magical property of a 2. Its half is always 4. How do we express this continuously? Let's imagine we want this to be a continuous number. What would be the equation? Oh my goodness, just over here. Great. Well, half of a number in this case is just the root of n. Yeah. This would be the number n. This would be root of n plus root of n. And then the other triangle, we have n squared, root of n plus n squared, except it's not. Unfortunately, life couldn't be that good. It's n minus root of n, which means this one is actually root of n minus root of n. Over here is actually incorrect. This is actually n squared plus n. Now, this is a root of n minus root of n squared plus n to the fourth, no, fourth, yeah, n to the fourth, n minus root of n. That's fun. We can check what these have in common here. We can check some stuff. For example, we can check x squared plus x root. Well, that's a funky looking. That's actually very neat looking. There's this hole over here. That's very interesting. Cool. Alright. And the other one, which is x minus x 2.5 to the squared then squared plus n the fourth, no then x. It's something. It's not really close, but I mean, what is close these times, right? Cool. This is necessary. We could divide both by these are different. Divide them by the same thing. Won't matter. We could divide them both by the area though. Over here, area would be just square root of x times x divided by 2. That's the area. Two sides of our rectangle that we divide in 2, which means times n squared over here should be, and over here it should be x minus square root of x. Why are they so close? I know why they might be so close. Don't know the exact reason though. I do know why they might be so close. They might be so close because I shouldn't treat them as triangles. I should treat them as what they are, which means we can check this except with finer definitions of triangles. So, okay, this is our first run, right? This is our first run. Now let's do finer triangles, which means we will have 2 over here, 2 over here, with sides. Might as well divide them on the halfway point, why not? This would be then 1/2 root of n. This would be n, except not. Okay, if we take it as 1/2 of on. Okay, if on 4 we get no, if on 2 we get a 4, then on 0. Then on 1 we get a 1. That gave me nothing. It will be just 1/2 will obviously be inside. Okay, so what we are actually looking for is a times h divided by 2 for a triangle looks like this. We have a and we have h divided by 2. So the entire area could be described like this, or it could be described differently with an integral. And every one like this, we go dx to the right, and we go dy up. My brain is mush, but I know we can describe it with an integral. It's like this. Let's just assume all of those are dx away, right? Except what we don't need this, we needed this. Slope! I'm such an idiot. That's obviously based on the slope. Which means we actually need to do something with the derivative to get the length of that side. Obviously we need to do something with derivative. Make it, you idiot! So obviously we need to do something with the derivative. How do we get that? Well, we could divide it into... Okay. Let's check those triangles, right? I know where we can find the answer, but I know it won't be satisfying. I go check that. All of those are just dy. All of these little triangles, this is a zoom into this triangle, right? Going up dy and to the right dx. Which means this is equal to a root of dx squared plus dy squared. And so what we need to do is we need to integrate that right there. We need to add, well, not integrate, we need to add all of them, all of these. Which means for x squared, this is fun, this is very fun. For x squared, if I'm not mistaken, that's 2x. Alright, so if we go function... Okay, if we take x squared, right? Wait, x plus dx squared, this would be equal to x squared plus 2x dx plus dx squared, and that's what, and this x squared plus 2x dx plus dx squared minus x squared, so 2x dx plus dx squared, that's equal to dy. That's what dy is equal to. Great. That's good. That's good. Believe it or not, that is good. We can get dy. Alright. But what exactly are we halving? Well, this isn't some what did I misspell? I am arbitrary. Calculus. Oh yes, that's great. I love that. That's a bold S. Doesn't seem like it, but anyway. Using calculus, and oh boy, who doesn't love calculus? We all love calculus, so let's get into it right away. I can't wait any longer. Let's take, oh my goodness, just don't help at all. Insert equation. Cut half of x, no wait, half of third, missed that almost, of x for example. I just realized I'm doing graphical interpretation of a root. Yeah? Kind of. Well, yes. Not kind of, just straight yes. Cool. Theory 1. Length. Well, not length. What would it be? Well, it is length. It is length. Yeah, it is length. Theory 1 length. So. First theory would be that whatever we are looking for is connected to the length. I would really like to add a graph here. It's kind of a problem. I want to add graphs, like neat graphs, not just a random screenshot. I could just, take a screenshot of this. I guess I could. We that's half of anything squared is just equal to its root. Yeah, it is. In relation to exponentiation, it's just equal to its root. We can, if we approximate if we have the function so that to get two different segments, first one from, let's just keep it here for now. First one from, let's insert an equation. First one from 0 This one from 0 to hot of x, or just x, and second from squarity of x to x, then calculate the hypotenuse of the right triangle Is it the right word? This looks so very wrong. No, my IP address! Gosh darn it! Hypotenuse, yes. I need to add a triangle shape. Oh, I love this. Please tell me Google docs add a function graph. Please. Chart. Please tell me I can graph function. That would be so sick. No, can I graph a function? But that's good. I'm looking for adding to a document in a cell. I don't really have a cell. Not Google Sheets. Oh, that actually looks pretty decent. No, I'm looking for fudge. I could add just Desmos screenshots, but that's not a great idea. I mean, I can. I can do it in Desmos like this, and then like a simpler way, like yeah, because areas are definitely not equal. Let's be real. We're looking for something that is equal, so we can just do Desmos define an area using 3 points. Yep, Masters Desmos. Oh my goodness. Isn't that a way to do it? My goodness gracious. Oh yeah, you know, just the way to draw triangles, you know, no big deal. It's just the way to draw triangles. I mean, my goodness. It's not. This is not what I'm. Not quite what I'm looking for. Connecting coordinate points, yes. So it needs more points. Makes sense, quite reasonable. A0, B0. Then we'll have A1, B1, and A2, B2. Can I somehow group them so that well, multiple points now, which is neat. Can't move them like that, but still decently neat. Now can we somehow So the table is still the best way to do it. Just add the table and 3 points I want to connect. Great, it's really useful to actually know the exact coordinates of all the points. Add a folder too for the, you know, triangle. Table. First we will have a 0, x0, y0, then we'll have x square root of 3, y3, wait no, y0, then we'll have square root of 3, y3. And now based on that, apparently we can create a polygon, just polygon function. Add expression over here, polygon x1 and y1. Great, so we have the first triangle, now all we need is the second one. Need two, because we need to copy all of this on the table. And we will start over here. No, there's two. There we go. Cool. This will be our original approximation. There we go. Just 4. No, that would be nice. And it's also smaller than 9. 3. I'm an idiot. There we go. It should be black so that it will be visible. Hopefully be on. No, that doesn't change anything. Great. Then, if we assume that both of both parts are just simple linear, no wait. Are just simple. How should I describe? Give me a second, alright? I'm back. Alright, I'm back. Oh, why is my... Oh, no, only 7,000 kilobits per second. Oh, no, only 8,000 kilobits per second. What's happening? Oh, okay, back to 12,000. Great. Yeah, I might be a bit overdoing it when it comes to kilobits per second. Or plus linear equation. Yeah, linear equation is just, yeah. Then just make this a bit smaller, like this. Then we assume we can calculate the hypotenuse of the right triangle. Of the right triangles. The first one, no, that's the image again. The first one equation will be equal to h1 is equal to that will be of x square t of x. No, actually it will be x. That's square root of x, and that's x, which means x squared. This would be our first hypotenuse, a squared, which is x, which is square root of x times squared. That will be x. There we go. The second hypotenuse, which is a bit more tricky, tiny, ever so slightly a bit more tricky, because this should be the fourth, because it's just x squared squared, so it's the fourth, and this would be x minus square root of x squared. Now those two are not equal. Unfortunately, imperfect word, very sad, not equal. Because the first one is relatively nice, looks pretty neat. Let me just get my decimals on the beginning, I might need it. There we go. First one is relatively neat. So this, wait, actually this I already changed one. Changed, no, that's not the reference to anything. In case anyone's wondering. Okay, great. And now if we just delete this division, we can see that these are all screwed up. X squared plus x, which is correct, yeah, and x minus square root of x squared plus, yes. Now these are no specifications, not estimate, no. Approximation. These are just approximations, but it is more convenient to do it first to actually check if there is anything worth calculating further. And in this case, there isn't anything worth calculating further. Worth calculating further, that's right, okay. In this case, there isn't. And we can right now just turn off more polygons. Also my points. Two functions are completely different. This looks very ugly. That's why I would prefer to insert those functions here instead of adding screenshots. Like, I don't know who even. Okay, that's the. Okay, this actually should be great. Are completely different. And the fact this is just an approximation is not a good enough excuse to still use it. Let me just do it like this. Over here I should also do it like this. Much better. A bit smaller like that. So something different happens though if we divide the hypotenuse by the area of the triangle. Oh yeah, it is groovy. It is groovy indeed. Oh come on, the image should be already up. There we go. And a triangle. Then the equations look like this. Because we just divide the area, right? And just make this a bit smaller, like this smaller. My goodness, why is it so hard to operate? Off. Nope, I need this. Just like so. Look like this, yes, which is closer. It is closer, right? If we move it a bit to the left, a bit up, yeah. Which is much closer. But Desmos, what did we divide it by? We just divided it by... Yeah, so we just take the original two equations for the hypotenuse and then change them to area. Area, by the way, over here it should be totally second. Hypotenuse. It will be so fun to do the same thing with integrals and the length. That's so fun. Let's change the theory. Let's just remove the theory from this. It looks very weird. Alright, great. Area first is this, except if it was... Can we just divide it? No, we cannot do it like that. Fine, no, not like this. Fraction. Fraction. Root of x times x divided by 2. Yeah, first this is root of x, this is x, yep, so of x times x.
More than 70 million people in the United States go to the movies each week.
Divided by 2.
Get away from their care and to
Oh wait, I've never heard this song before.
romance and
To the movies.
on the magic screen.
Trust me, I know Chap pretty well, and I've never heard this. Now the second area would be equal then to... no wait, this is not area. This is... This is length hypotenuse divided by area. H2. In this case, we just have to divide by area, which is well, divide by 2, and over here on the bottom we have x minus square root of x times x squared. No point in this being so small if, you know, we have all the space. Look like this. And now we can see that shapes of these two functions are quite similar. Which means it is finally time to do it properly. First of all, the area will be obvious. We can see that the shapes do it properly. First of all, area. Area is calculating the area is rather simple because we do have a very specific calculus for this. Wait, I think this used to be the first song. No, it wasn't. I thought it used to be the first song on the playlist. Another Sunday for me. Alright. Made for this. Integral. And over here it would be so simple. I mean, area of the shape 1 will be will be equal to an integral. It's honestly so easy. It's an integral from 0 to of x. I can see the issue now. I can see the issue. Well, I don't actually. U squared du. Yeah. Yeah, because over here these were these at 3 is what we would have gotten, right? 3. So over here would get 9, around 9. Yeah, a bit over 9, and over here would get wait, x to the 4th. Yeah, this is around what we've gotten. I'm not certain actually. Yeah, this is equation for hypotenuse for any x, so yeah. U squared du. Yeah, rather simple integral, and then the second one, area 2, would be from x squared to x. Rather simple. Second, length. Calculating length will not be as easy. Fortunately, if we have the slope, can we calculate it based on the slope? Okay. dy divided by dx. dy divided by dx gives us a slope, right? And dy... what does that mean graphically though? I can... Let me just... Okay, so this, right? If we have this triangle, is dy up dx, and we are trying to calculate this actually, which is equal to... Obviously, okay, great. Length. If for any point for this derivatives will be extremely helpful. For any number a, no, this is usually used for constants, delta, alpha, I don't really want to go into the Greeks yet. For y, no, that's the height, x we already knew, u is taken, v, w, mn, n is taken, but m, for a number m, we will need to calculate dy and du. Wait, if you have du, shouldn't you use... No, dv is just for another one, right? If you have two, yeah. We already used x everywhere and properly. Please do note, no, in this case, instead of using x to represent our original half number, we will use u. And so in this case we just have to change them up, so this would be u, this would be u, this would be u. This would be x, dx, x, dx. There we go. Dx. Which means that we just calculated the good old-fashioned way, x squared is equal to y. Now x plus delta of dx squared is equal to y plus dy, in which case x squared plus 2x dx plus dx squared is equal to y plus dy. Then all we have to do is just change this for x squared, then the usual stuff, which means take this away, take this away, and there we go, we have dy. Cool, am I right? We have gotten ourselves a dy, which is fun. I feel like this is such an easy problem and I just cannot solve it for some reason. 2x dx, no, that's good enough. Such an easy problem, I can't solve it. So we have the side, this, now all we need is the based on that we can create a little triangle. So for every dx, our y, every dx added to our x, our y gets dy bigger. If we go dx units right and dy units left, up, not left, up, then we can connect our starting point and our ending point to get another hypotenuse. That's so weird, looks so dumb. I'm sorry. Sorry, just anger. Which means that, oh my goodness, this will be fun, wouldn't it? Won't it? It would be extremely fun. Dx is approaching 0, right? That would mean we'll have to get the integral of that approaches 0, right? I think so. Which means let's call it H. Or DH, that sounds like fun. DH would be then equal to S squared t square root of dx squared plus 2x dx plus dx squared. Which I mean looks like loads of fun. Let's expand it, why not? Oh my gosh. That's great, no, that's great. So over here we'll have this squared plus 4x dx the third, right? Yeah, plus the fourth, if I'm not mistaken. Just loads of fun, honestly. I mean, it's loads of fun. Yeah, now what we can do is do this 1 plus 2x dx third plus dx fourth, which is it's great. No, it's great. That's the same equation, right? 2x dx squared, yes, plus 2 times. It's a sane equation. It's very sane. But that's the height of what happens. Now all we need to do is add all of them in there as dx gets closer and closer to 0. But you know, it makes no sense. It makes no sense. It makes no sense. I mean, in order to add all of them together, we would need to take the integral of something. The only question is of what. This could be a function describing our hypotenuse function at every point. There's x in there. Why is there x and dx? It's insane. I mean, dx gets closer and closer to 0, but if we say that dx is closer to 0, a limit of as dx is closer to 0, then we are done. Because then... well, yeah, then we are done, because then all of this goes to 0, no matter what we do. We have dx squared, dx third to the the third power, and dx the fourth. What are we supposed to do? We have to keep dx there. Yeah, we do have to still keep dx there. You cannot say that dx approaches 0, because then it breaks. And it dies, so... ha 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 ha. It's fun, it's really fun. Calculus tool, because I'll look like a fool. I mean, at every single point x, at any point x, for a given dx, this equation will describe yeah, at any point x, this equation will describe the length that it traveled. If that makes sense. Doesn't make sense. Who am I kidding? Doesn't make sense. How would this make any sense? Wait, the derivative describes... is dy divided by dx, which means derivative doesn't actually describe the slope. Well, it does describe the slope, right? But it describes to us... it describes to us the relation between the height and the length. But yeah, still only one way to get the hypotenuse. Hypothesis is what we need. We need to add all of these hypotenuses. How can you do that? Well, good question. You see, we would need the graphical interpretation of an integral. Free blue and brown? I guess? Damn, that song is good. That song is so good. Okay, I have only one solution for this. Why am I not subscribed? Oh yeah, because I forgot again, no new account. Subscribe. The more you make, fudge off, Elliot. I always have the same reaction to this comment. But this is a very good comment. I like it. Subscribe. Subscribe for a cookie. It's an, well, it's not really an inside joke. It's a banner that Soda had an account. Yeah. I need the graphic. I'm sorry. I would love to watch it all. I watched it all multiple times, but I can't watch it on stream. That'd be freebooting. Not doing that. I'm pretty certain I had a shield, anti-freebooting shield somewhere. Yes. So it's our function times... Okay. Alright. Oh yeah, I'm such an idiot, obviously. So it's just the sum of these, yes. An integral means just every single one that there is. It's very surprising. I'm like trying to think. Okay, so what we are trying to do, I don't think that's right. So we have this function again, right? What does it tell us? It tells us for any point. For any point, it's instant length. It makes no sense for something to have an instant length, but that's what it tells us. So all that we need to do is we need to add all of them, which stinks. It stinks like an integral. It just, the smell of an integral in here, it's just insane. So why, how, who? What if you do it a different way? So h would be equal to this, right? Yeah. H would be equal to this. What about dh? What if we do integral h dh? Then we would need, well, yeah, h dh. because integral h dh integral h dx. Yes, it's integral h dx. It's psychotic, to say the least. It is psychotic to say the least, but integral of h dx would make sense. That's kind of what we are trying to figure out. Because then what we would do is we would take... Actually, wait. If we have this, right? Let's divide this by dx. Dx squared plus dy squared divided by dx. Now we get a ratio of this to this, which means if we multiply this ratio by dx again, what we get is this. But what's really neat about that, well, oh, that's just... No, wait, that's not the derivative. Derivative would be if we divide it over here. There's a derivative of a different function. What if we take the derivative of the hypotenuse function? Yeah, what if we make a function for the hypotenuse? No, it wouldn't work. I'm sure I can insane person. How does this look, by the way? Yeah, like an insane person stuff. Great. Music is great though. Bucky keeps... Oh, that's not... Oh, chop. That's not chop. See, by the way, I promised the long streams would be back, and look at that! 4 hours! Oh my god, 4 hours. I spent 4 hours on this. I have so much more things to do. So many more things to do, actually. Because it's countable. 8 to be exact, well 7 now that I've done the first one. But I can't let it go, it's too cool! Gosh darn it! Okay. X plus dy. I can't let it go, I don't know how to. I don't know how to let it go. How am I supposed to let it go? I have to calculate. Gosh darn it! Ah, so annoying. So annoying. So annoying. So many numbers here. Flowing in my head. I have to pick the right ones. I know which ones are the right ones. Just... I need a Watson. I need a Watson next to me right now. I need someone to whom I could explain this, so then I would see if it makes sense or not. If it does make sense. I need a Watson. If we divide it by x, dx, I mean, then that gives us the ratio of this to this, which means a number that if we multiply the x by, we get this. So then, if we have that, we know at each point we know at each point how much more there should be than there is. I don't understand it. If we have a function, right? It has height and length. This at each point like this. Well, I just like this straight line, so at each point, right? each point, it tells us we take this length, right, L, we multiply it, so L times H, and we get the actual L, the big L, the L that we are looking for. Then if we sum all of them up, so if we take that's integral. If H is a ratio, now if we take the H and divide it by dx, we get a ratio of the of the length at any point of the sideways length at any point to its actual length at any point. And right about now, someone could tell me that I'm insane talking about lengths at any points. Any points, but it's calculus. Slope at any point makes just about as much sense. So now that we have this, oh my goodness, this will be fun, won't it? And so if we add together lengths at all points multiplied by the length to actual length ratio, then we should get the actual length of any half, and it should look something like this. Yeah, this is let's call it L1 and L2, and it will be the same thing except this will be H, which is insane. I actually would like to copy this and then go on my Discord. Top 10 math sentences. Yeah, I'm posting on my Discord. It's funny. It's funny though. Expanded, it would be still madness. I'm not very hopeful at this point. I don't think it will work. I think I'm just going to plug it into Wolfram Alpha, and Wolfram Alpha is going to tell me that I'm an idiot. That's what is going to happen. So, here goes nothing. Wolfram Alpha. Hi there. Could I please, thank you, get this? Great. So math input, it's an integral from 0 to a square root of u dx of square root of dx squared plus two times x times dx plus dx squared. What do you think about that? Would this work? Oh, is it from alpha going to tell me I'm an idiot, or is it going to assume that d is a constant? X squared. Definitely has integral square. What now? What? What now? What? Wait. Integral square. Why? There are so many more things in there. Okay, option 4, I broke Wolfram Alpha. Did I break Wolfram Alpha? Okay, is there... Well, there has to be some sort of definition, very rigorous definition of integration, right? From a to b of f of x dx is equal to... For convenience of computation, it's very okay. Each subinterval has length b minus a by n. Makes sense. Yes, makes so much sense. That's index, so a plus... Yes, that is true, yeah. So now we can define it as Anyway, now we can make this a bit shorter. We can just take an infinite sum, right? This would be... We'll just plug this over here. Plug this over here. And make n equal to infinity. I would really like to see that. Definite integral is... Oh! For I divided by n. Alright, so for I divided by n. There's the, oh, that is very neat. That's a very neat solution. I like that idea. Well-known summation rules, yes. Except my integral might be a bit more complex. But I like the idea of defining dx as b minus a divided by n. Now, let me just change that to... We will have to be really careful solving these integrals, considering how many dx which all approach 0 are there. What I could do is I could genuinely include that, because b minus a divided by n, yes, that is genuinely what it is as n approaches infinity. That is true. I just really hope that I didn't get the h wrong. If I did, oh my goodness, I am dead. H is the hypotenuse divided by ratio of so h divided by dx times dx, that's just h, leaves us with h. Yeah, it does. Just leaves us with that's the ratio. Actually, I'm good with 2. This is great. It's great. So we can solve it the slow way. How many pages? But we've written 6 pages on the day, and all of them so far are correct. There's nothing. There's nothing that's no proof or anything. No, everything that I say is true here is true. This is still. I'm still proving this, but I never said that it's true as it is. No, we're not prove that though, it's true. Why are we doing this, by the way? Oh, we are looking for what halving means. Yes, what taking half means. So that in the end we can do this. Which I just hope. I don't know, I'm doing halves actually. I remember it had something to. Yeah, it's good enough. So we should start by considering what actually. Wait, no. Wait. H should be a function of x, because there's x in there. There is. H is a function of x that for any x gives us its instant. This time H is a function which gives up. Yeah, that's me. I'm just running what's on my mind. Gives us an instant hypotenuse for any given x. Instant hypotenuse, it's madness. It is just madness. But you know, might as well, right? We're having fun. We're partying. So any given x, yep, it we give it an x and it returns an instant hypotenuse. Yes. Which means we don't need to divide it. About a hypotenuse at any point. It's kind of slope. Any point makes just sense. Yeah. So we didn't have to divide it by the x. We can just use it as a function. H of x. Yes. Great. Ah, that's sick. Is it the same dx we're talking about here? No, it is not. But this has to be the u. Okay, this has to be v and dv. Oh, this is so insane. Great, so we right now have a function. Yes, I mean, we are closer. Don't get me wrong, we are closer. It's just, we're closer in the kind of wrong direction. Oh, this is great. I mean, dv and dx in theory equal to the same thing. In theory. This is madness. This is just straight up madness. Well, we can use dx here, right? Actually, we can use x. I think. Can we? I don't know. If I make a mistake right now, it would be horrible. Well, it won't be that horrible. From now on, it will be just wrong. So I could redo that. Is having dx's in a function a bad idea? Yes. Will I care? No. There. So step by step, let's do it very carefully. Very, very carefully. First of all, this goes over here. This already doesn't seem that careful, but it is, so far it is, yeah. Now what we need to do is remember what dx equals. The x equals u squared minus 0 divided by n. Oh boy, this is fun. Aha, ha 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 ha. Oh, the function returns 5 no matter what. You give it. Okay, yeah, I get it now. So this is a boring example. This is an interesting and juicy example. Oh boy, it's an interesting and juicy one. That's the 5. Now we have this. 1 minus 0, because yeah. Delta xi is equal to this, yep. Ci is equal to 0 plus this times I, which was just equal to I divided by n, great. Function of x is equal to 2x plus 3. My case is a ton more complex. I am okay. I am not really used to solving integrals that look like this. Okay, Wolfram Alpha, tell me, what happens if there is like... How could I... Okay, up to 2, let's say. Why not? X... Like this. What happens now? The x plus x. Is it normal? No, that's not. Okay, so having dx's in here is not normal and will be problematic. It is so not normal. Fudge! I am effed very, very badly. I don't want you to interpret it as that. No. That's not quite the case. Times x. How about this one? That's a problem. That's a problem. Ha. Ha. So we are looking for something which derivative. Actually, wait. Is this a problem? It might not be a problem. When you have derivatives, when you derive them, you divide both sides by x, dx, and then you take the limit as dx approaches 0. But if you won't take the limit, dx's are still there, which means derivative of x squared is equal to 2x plus dx, so dx's are there. Now, when you are trying to solve an integral, what you are actually doing is just finding an anti-derivative derivative, which means a function which derivative is equal to integral. You might think that it is madness because inside our integral we have many, way too many, as some might say, the x's. But the truth is, when you look for a derivative of something, you still end up with those dx's. Yes, they just disappear when you apply zero. So we just have to find a function which, after being derived, would give us this. Which is easy, you know, why not? I mean, why not? Why not? That's a possibility, right? That's a from alpha. What happens if I do dy is equal to this? To what happens if I say dy is equal to? Wait, squared? No, that's dx squared plus 2x times dx plus dx squared. Interpreting a square. Interpreting a square. Thank you. Thank you so much. I'm so glad you interpreted it as a square. I mean, how hard could that be, right? Just find the function, which derivative, like this. No biggie. Just no. Actually, that could be doable. It is very annoying that x is multiplied by dx. If it wasn't multiplied, this would be actually relatively easily doable. I'm saying relatively easily. It's not that easily. So let's look for a function so that oh boy, this will be fun. Divided by dx. Well, I'm pretty certain in normal definition there's just divided by h. As h approaches to 0, There's a no definition this h as h operator 0, but we'd have to do dx. Be more correct. Great. No, this is really fun. This is very fun. We could multiply both sides by the x. I mean, at this point, might as well. I'm out of ideas. I don't know. I just simply do not know. Dividing by dx on both sides is ridiculous. I guess maybe expanding this. This should be as h approaches 0, but let's just do an m because h already means something else. Oh wait, actually no, it can be dx as dx approaches 0. Anyway, I guess that'll be it for this lesson. We did quite a lot, so let's refresh table of contents. I guess that'll be it. It was fun. So, I'm just going to wait for the end of the song to actually time it correctly. We did quite a lot, but for now that'll be it. Thank you everyone so much for watching, and have a great day. Bye.